Hello, students. Welcome back to Unit 2 Basic PLC Programming. In the last session, we went through various types of logic gates and how to convert a logic gate into a ladder diagram. And in the last session, we also discussed some of the rules to be followed while doing the conversions. When there is an AND gate, the inputs of the AND gate are represented as contacts in series, whereas the OR gate inputs are converted into the contact are converted into contacts in parallel. And I also told you that um, and we also went through that we also saw that any start button, if there is a start button, it can be represented as normally open contact. And if it is a stop switch, in that case it has to be represented as normally closed contact. So by keeping all these rules in mind, now, in this session, we will see, given a logic circuit, how to convert that into ladder diagram. Then we'll analyze a conveyor control circuit. Then we'll go through motor control circuit and a process control circuits. Now we'll go to the first example. This is a simple example I have taken here. You could see here in the logic circuit, we have used only three gates here. Now we'll deal with how I can convert this logic circuit into a ladder diagram. Here, the situation is that they are okay, 7, 8, 17, 18 are the four inputs. 122 is the output of a logic circuit. And I've used two AND gates and one OR gate here. So the condition is that the output 122 is to be on only when either input 7 and 8 are on, or when all the four inputs are on. Uh, Here in the problem statement, you should be very careful when you are reading a problem statement. Here, and, or, either, or, these things matter a lot here. So he says the output 122 is to be on only when either is here. So either means there are two conditions. So when any of the two condition is met, your output will be turned on. So it says that either the inputs 7 and 8 are on, or all the four inputs are on. So here I've taken 7 and 8. When any one of them is on, when either out of these two inputs 7 and 8, when any one of 7 or 8 is on, and one output will be 1, and the output 122 will be 1. Similarly, the second condition says that when all the four inputs are on, so I have taken the input 17 and 18 also and connected to AND gate. When this 17 and 18 both are on, 17, 18 are on, then AND gate output is 1 and the OR gate output 122 will be on. And here also, here input 7 and 8 both are on. In that case, AND 1 output is 1. And when 17 and 18 inputs are on, and 2 output is 1. And I have taken a OR gate here. This either represents is represented as OR gate here. So this OR gate output will be on when any one of the outputs of AND 1 and 2 goes on. So Now I'll convert. Now the logic circuit have written. First, you will be having a problem statement. That problem statement has to be converted into a logic circuit. After that, that logic circuit is converted into a ladder diagram. So there are, you can see the steps of conversions. A statement is given, a practical problem statement, convert that into a logic circuit, then convert logic circuit into a ladder diagram. So here I have for and 1, I have two inputs 7 and 8. So I have taken the contact ion 7, ion 8 because they are the inputs of AND gate. So they are in series. Similarly, I have AND 2 input 17 and 18. So they are connected in series, the contacts in series. Now you can see you have OR3 gate. The inputs are coming from, for an OR gate, inputs are coming from AND 1 and 2. So the inputs of this OR gate, they have to be connected in parallel. That's why I have taken this combination and this combination in parallel with each other. Now that is given to our output coil called 122. Now we'll analyze whether the ladder diagram works for the problem statement. We'll assume a case when all the four inputs are on. In that case, the output coil should be energized. So when I take a case that all are energized, when all the contacts, four contacts are energized, in that case, ion 7 and ion 8, when they are energized, they close. Similarly, 17 and 18 contacts, when they are energized, they will also close. So there is a connection between the two power rails. A connection is established between two power rails, and hence the output coil 122 will be energized. Now, I'll assume a second case that 7 and 8 inputs are on. So, when I energize contact 7 and 8, they will close. So, thereby you will have a connection between the two power rails, and hence the coil 122 will be energized, thereby producing the output. So my problem statement condition is also met. It says that when all the four inputs are on, the output should be on, or when input 7 and 8 are on together, the output should be on. And that condition is met in the ladder diagram. Next, we'll move on to another example. Here we are using a conveyor. Now I want to start and stop a conveyor belt here. So this is basically a conveyor control problem here. And the condition is that conveyor C is to run when any one of the four input is on. It is to stop when any of the four other input is on. That is, I have a conveyor, and conveyor will run when any one of the four input is on. That is, input 1, 2, 3, 4, they are used to start running a conveyor. Whereas there are other four inputs you have 11, 12, 13, and 14, and they are used to stop the conveyor. When any one of the stop switches are energized, then conveyor has to stop. I think problem statement is clear now. So I'll repeat the problem. You have a conveyor. I need to control the motion of the conveyor belt here. And there are four start switches. When any one of the start switches energized, conveyor has to start. And similarly, I have four stop switches. When any one of the stop switches is energized, conveyor has to stop. So this is the problem I'm having. So first what I'll do is convert that problem into a logic circuit. So here I have done a logic circuit for you. Here you can see here, uh, and in previous classes also I told you about, for start switches we'll be taking normally open switches, and for stop buttons, normally we'll I mean generally we'll be taking NC switches, normally closed switches. So same thing I have used here. So this OR gate, for the inputs of an OR gate, you can see here. Here I have connected normally open switches. So it's a four input OR gate, because I've got four start buttons, and those start buttons are represented as normally open switches, called 1, 2, 3, and 4. Then for to represent stop buttons, have taken normally closed switches, and this you can observe here as an input of and 2 gate. Here I've taken a normally closed switches here, called as 11, 12, 13, and 14. And the problem says that when any one of the four start button is on, in that case conveyor has to start running. Now we'll see that. I'll assume a case that your start switch 1 is energized. In that case this switch will close. When this closes, because this is an OR gate, so when any one of the input is turned on, the OR gate output will be 1. So here you will be having 1. And at the same time, you could see here this stop switches are taken as normally closed switches, so they will be closed, and hence the AND gate, the four inputs of an AND gate are all turned on, hence AND gate output is 1. So here you have 1, and the OR gate output is also 1, hence the output of AND 3 will be 1, that is C will be turned on. So this is the one part. And coming to the working of the stop switches, assume that your conveyor is running. So now what I'll do is I want to stop a conveyor. Hence, I'll energize the switch 13. So when I energize the stop switch 13, it opens. When it opens, because it's an AND gate, when any one input of an AND gate is 0, the output automatically goes to 0. Therefore, AND 2 output will be turned off, it is 0. And AND 3 output will be 0. Hence, conveyor will stop. Now, next, let us move on to how to convert this logic circuit into a diagram here. So this OR gate inputs, as I said, the OR gate inputs are converted into contacts in parallel. So I have taken IN1, IN2, IN3, and IN4, four contacts which represent the start switches, and they are connected in parallel. Next, we'll see about this and two inputs. Here we have the stop switches. So these four stop switches are represented as four contacts in series. So you have IN 11, 12, 13, and 14. These are the four contacts that are connected in series, and this combination represents an OR gate. This combination represents the AND gate. Now these you have AND 3 and 3 inputs. One input is coming from R1, and the second input is coming from AND 2. And because it's an AND gate, so this inputs for the AND 3, they are to be in series. So you can see here, this is one combination which represents the R1, and this combination of four contacts, they represent a and 2, and these two are connected in series, and that represents your and 3. Now we'll assume how, we'll see how this ladder works. Let us start the conveyor. So what I do is, among these four start contacts, I'll energize any one of them. Let me energize IN 1. In that case, IN 1 will be closed, and anyhow these stop contacts are normally closed. So as long as it is energized, it remains to be closed. Hence IN1 is closed, IN11 is closed, 12, 13 and 14 contacts are also closed. So there is a connection established between the two power rails, and the coil CR20 is energized, and your drive for the conveyor is connected to the output of the coil CR20. So our conveyor starts running. Now I'll take the second part of it. I want to stop the conveyor. In that case, what I'll do is, let me energize the contact IN12. So when I energize IN12 contact, it opens because it's a normally closed contact I've taken. When I energize this contact, NC contact, it will be open. So when IN12 opens up, there is no connection between the two power rails, and hence the coil CR20 is not energized, and hence your conveyor will stop. So next, let us move on to the third example, and it is a motor control circuit. Here we'll be using two start buttons and two stop buttons. The condition says when start button is depressed, the motor runs. By sealing, it continues to run when the start button is released. Either stop button stops the motor when depressed. The system seals on when the start is released. So here you can see the sealing concept is used here. Okay, then first let us derive the logic circuit here. So here it is again. I have taken this. I have followed the same convention that for to represent start buttons, I'll be using the normally open switches and normally open contacts, and to represent stop buttons, I'm using normally closed contacts. And here you can see the output is D here, and this output is again fed back as an input of an OR gate. So this represents a sealing concept in the logic circuit. And here you have 11 and 12. These are the start buttons, whereas we have buttons 1 and 2, which are used to stop the motor. And sealing is shown as an feedback from D output to the input of OR gate. And here you should observe that these start contacts, they are connected as inputs for an OR gate, because the condition says that whenever any one of the start button is depressed, the motor has to start. So when it says any one means you have to use a OR gate. So when any out of two start buttons, when I energize any one of the start buttons, in that case, suppose I energize the start button 11. In that case, the contact 11 will be closed, and since it's an OR gate, when any one input is on, the output will be on. So the OR gate output goes 1 here, and here you see these stop buttons, they are taken as normally closed switches. So the AND gate, all the three inputs of AND gate are turned on, and hence the D output will be turned on. And this D output, I am feeding it back to the input of an OR gate. So this will be 1. In that case, now think that I am releasing the start button 11. In that case, one of the input of an OR gate will be 1, and hence the output of OR continues to be 1. That means even though I release the start button, um, the motor continues to run. So this is known as a sealing concept. And here you see for the stop buttons, I've taken normally closed, and then they are connected to as inputs of an AND gate here. Now let us go to the conversion of this logic circuit into a ladder diagram. Here you see you have AND gate here, and the inputs are 1 and 2, which represents a stop button. So because it's an AND gate, the inputs are to be connected in series. So I have taken IN1 and IN2 contacts, which are connected in series here. Now let's move on to the OR gate here. We have here three inputs for the OR gate, and since it's OR gate, the inputs of OR has to be converted into contacts in parallel. So I have taken three contacts and are in parallel with each other. You have 11, 12, and one more contact IND, you could say. So all these three are in parallel. So it represents a OR gate here. And here I have a contact by name IND, which represents your sealing contact. So here also, whenever the D coil output is energized, the contact IND will be closed. That is, whenever the output is turned on, the contact seal contact will be closed. And even when I release these start buttons, your circuit, I mean, there will be a connection between the two power rails through the seal contact. Now we'll see how the ladder diagram works. So, I want to start a motor, so I'll energize the start buttons. So in that case, let me energize IN11. So when I energize IN11, this contact will close, whereas IN1 and IN2 are normally closed contacts. And in case I am energizing IN11, even that also closes. So there is a connection between the two rails, and hence the output coil will be energized. So the motor starts running now. Now think that I'll release the start button. When I release the start button, because this output is energized anyhow, and because it is energized, and you have a sealing contact here, and whenever the output is energized, the sealing contact will be energized, and it closes. So thereby you will be having an alternate path through the seal through IN1, IN2, and sealing contact. Hence, the motor continues to run even though I release the start button. Okay. Now I want to turn off a motor. In that case, I will energize the stop contacts IN1 or IN2, any one. So let me assume that I energize IN2 contact. In that case, IN2 contact will open. So when this opens, there is no connection between the two power rails, and hence the coil D is not energized. Thereby, the motor stops. Next, let us move on to another example of a process control. And here I have a process fan here, and I mean, a process fan, it has to run only when all of the following conditions are met. So there are four conditions. When all the four conditions are met, the fan has to run here. So the first condition says the input 1 is off. Uh, The second condition is input 2 is on, or input 3 is on, or 2 and 3 are on. The third condition is inputs 5 and 6 are both on. The condition 4 is one or more of inputs 7, 8, or 9 is on. So when all the four conditions are met, then a process fan is to turn on. Here the first condition will take up. A process fan is to run when input 1 is off. So when input 1 is off, your process has to be turned on. So I'll take a NOT gate here, and 1 represents the input here, and I've taken a NOT gate here. So whenever this input is off, 0, then fan will be running. So the input is 0, the output of NOT will be 1, and this is used to run the fan. Now we'll look at the second condition. It says input 2 is on, or input 3 is on, or 2 and 3 are on. So this condition, it looks like, I mean, it resembles your OR gate. When any one of the input of an OR gate is on, the output of OR is 1. Or it is on when both the inputs are on. So I'll take an OR gate here, and the inputs are 2 and 3 I have taken. The third condition is that the inputs 5 and 6 are both on. So here it is given that both are on. So both means you have to take a AND gate here. So I have an AND gate here, and the inputs are 5 and 6. So when 5 and 6, 5 is also on, 6 is also on. In that case, a fan has to be turned on. So I have taken a AND gate here. The fourth condition is that one or more of inputs 7, 8, or 9 is on. So this resembles your OR gate condition. Hence, I've taken an OR gate here, and the inputs are 7, 8, 9. So when any one of 7, 8, 9 is on, the output of OR is 1, OR is 1, and your fan will run. And at last, here I've taken an AND gate here, and which has the four inputs coming from NOT gate, OR gate, AND gate, and another OR gate here. He says in the problem, a fan is to run only when all the following conditions, all is given here. So in the problem statement, all means it should be, I mean, all the four conditions are to be matched. That is, all represents a AND gate here. So here I will take all is given. So this all represents, you have to take a AND gate. When they say in the problem statement any one, in that case you can use a OR gate. And when they say all the conditions are met, in that case we have to use a AND gate. So I think this gate diagram is clear to you. Now let's move on to a ladder diagram, how I do the conversion here. You see here, this is a NOT gate. Okay, so this is represented as normally closed contact, because in the first beginning session only I told you about whenever an input of an AND gate is bubbled, in that case, that input is represented as normally closed contact. So here the input of AND is bubbled here. Not means you are bubbling, you are doing the complement. So it is represented as NC contact. Then we have OR gate here. The two inputs are 2 and 3. So these 2 and 3 are contacts are connected in parallel. Then we have an AND gates. The inputs are 5 and 6. So the contact 5 and 6, they are in series. The last gate we have is the OR gate, and the inputs are 7, 8, 9. Hence the inputs of OR are represented as contacts in parallel. You can see here. And at last we have the AND phi gate. So the inputs of AND phi, they are to be they are to be shown as contacts in series. So hence this is the output of a NOT gate. This is combination represents output of OR gate, and this combination of contact 5 and 6 represents an AND 3. Then we have a combination of contact 7, 8, 9. It represents OR 4 gate. So all the four outputs of the gates, they are to be in series. So hence they are connected as input for an AND gate. Hence they are the combinations are connected in series as shown in a ladder diagram. So in the next session, we'll see more practical examples like this. So thank you.